Well, we've just heard some wonderful lectures on RNA, coding, replication, evolution, but we still have this problem about what was the first engine, and indeed, what was its fuel. So I'm going to suggest that we should think about what life does rather than what it is to understand that. And what does life do? It hydrogenates carbon dioxide right down the bottom of the food chain and probably down the bottom of the evolutionary tree. It hydrogenates carbon dioxide. So presumably, that's how it started. So here's what I'd like to also emphasize, and people have already worried me about the remark about entropy, but I think we shouldn't forget this wonderful book by Schrodinger. To me, there were two wonderful books about the origin of life. One's worth reading, and it's by Leduc, and by the way, it's a century to when it was published. It was published in 1911. It really is worth a read. He had the Nernst equation, all the kind of things in it that, in fact, I'm going to allude to. The only thing he didn't have was an alkaline spring. But taking the other book, of course, and that is What is Life, and that's from Schrodinger, I'd just like to emphasize, he kept on saying, what does life do? It drinks orderliness from a suitable environment. So, yeah, let's find with this suitable environment. What is a suitable environment? It's got to offer us everything, all in one place. We don't want any contingencies. It's got to be right there. Nothing, no false pleas. So, our suggestion then is basically, we're looking at an Earth which is a water world, and I'm going to go back onto that, but there's probably at least twice as much water on the early Earth, probably more than that. There is no land. The day lasts about 12 hours. The moon's much closer. The galaxy's probably much closer, and the other galaxies are closer. This is a different planet. Don't think this planet. Think another planet. It's a third of the age of the universe ago. So, and of course, we've got the water covering the planet. It's a pretty oxidized surface, don't forget. It's H2O and CO2. And without photosynthesis, you can't do much better than that. So we've got an oxidized exterior, and we've got one compartment on this planet of water. So, but we need to think about how we could get some tension on the planet, because after all, what we have is water we know can descend into the planet and, in fact, oxidize the surface, or the near surface, oxidize it, carbonate it, and hydrate it, so much so that this water up here, which probably supports up to 10 bars of carbon dioxide and maybe more. Don't forget, Venus has 90 atmospheres of carbon dioxide, so we're not claiming much, and as somebody said yesterday, Mars has a carbon dioxide atmosphere. That's what these planets are like. At high temperature, through volcanoes, you get carbon dioxide. So that's the exterior, but the interior is electron-rich. Down comes the water, and suddenly we're getting a differentiation of this seawater, which was somewhat acidic up here, carbonic, if you like. It comes down, and then it comes back up, and it's quite different now. It's got a pH of about 11. It's got quite a lot of hydrogen, so that's our fuel. It's our favorite fuel, after all, what we're all trying to aim for. Some methane, not such a bad fuel, and some formate. So this is coming up now, and it's like a titration. This water now is going to come up. There's 5 pH units different. It's going to come up, and it's going to titrate into this ocean. But as many of you, at least when I was young doing buretting, you'd know that out of a burette or even a pipette, you'd get some fouling. And here we've got some fouling, and it's inorganic fouling. This is all about an inorganic world to start with. So my molecule, prebiotic molecule, what I think about the prebiotic molecule, it's carbon dioxide. So we're bringing this material back up here, this water back up here. We get some fouling, we get some frustration. We get this, therefore, becomes the kind of creative place for interaction between the carbonic ocean and the hydrogen. And this is where we would say hydrogenation of carbon dioxide would start. And if we kind of blow this up a bit, we've got our iron sulfide and iron nickel sulfides. The iron, by the way, coming out of this reservoir of an ocean. And I'll explain that in a moment. Some nickel, of course the CO2, and protons. So we've got even a proton gradient. So we've got a proton motive force, but also we've got things like nitric oxide out here. So we've actually got a redox gradient as well. And the overall amount of energy is about between 0.5 and 1 volt. So it's a commensurate energy with what we use today, so what life uses. And we would suggest that life starts probably between 40 and 80 degrees centigrade in such a system, a compartmentalized system. So I call this a two-compartment entropy trap, because we've had one compartment up here, which was, of course, the open ocean, and then we can differentiate that water and bring back the water, and now we've got an entropy trap because we've got these two fluids constantly interacting with each other. So here's this turbulent water world, the Hadean water world. It's a single compartment, as I say. It's got 8 times the amount of UV present day. That you wouldn't want to be on the surface of this planet. I mean, it's really a hopeless place to be. There's no land to stop the hurricanes. It's continually out of physical equilibrium as well as chemical equilibrium. So it's a turbulent world, the Hadean water world, and as I say, and it's being impacted, of course, by bolides. And after the lunar impact, the ocean probably rained out around about 4.4 billion years ago, and life would have started very shortly thereafter, and it would be very hard to kill after that. And I think that life probably started around about 4.4 and kept going. So we know now, and of course we're getting yet another experience of this from Iceland, that here's the volcano. This is last year's volcano from Iceland, and of course out comes this carbon dioxide, some hydrogen sulfide, sulfur dioxide, trioxide, nitric oxide, plenty of nitric oxide, not just because of the lightning, but because nitric oxide is stable in this magmatic material. There's an interesting crossover geochemically, so that really, the state of carbon in the mantle would at low temperature, would like to be methane. But around about 400 or 500 degrees centigrade, there's a crossover between the redox condition of iron 2 to iron 3 and methane to carbon dioxide. So at high temperature, you always get carbon dioxide. In fact, geologists since Darwin have always known that the early atmosphere of this planet was carbon dioxide. So here's our Earth, and as I say, it's oxidized on the outside. It's even probably got some ferric iron, and yet the interior is reduced. It's, in fact, it's a little bit of native iron and some ferrous iron, and that's the material that basically is oxidized by water to generate the hydrogen. So hydrogen becomes the carrier gas, if you like, of the electrons from the interior. And actually, it's a bit like an autotrophic bacterium. It just doesn't do the job fast enough, but it does make some methane, as we know. So it can do that. So we could think of this, and I don't want to take this too seriously, because I don't think methanogens were very early anymore. But basically, here's the reaction, and the world can do it pretty well geochemically. Hydrogen plus CO2 makes methane plus water. So we can think of this a bit like a methanogen. Here's the methanogen, or an electrochemical cell. The output, as I say, between 0.5 and 1 volt. So what we'd suggest then is, can we imagine life kind of bubbling off from the surface of the planet? And here we suggest that just as a bubble, here's the kind of inorganic membrane that I hope to show you. Inside is very low pH conditions, very high pH conditions, very low hydroxyl, very high hydroxyl amounts, and on the outside you've got the protons from the protonic ocean or the carbonic ocean. And so we've got a kind of entropy trap here because we've got continual order between the inside and the outside. This is reduced and this is somewhat oxidized on the outside. And as I say, it's rather like bacterium, except that bacterium transports the protons out of the cell to come back in to drive things like ATP, whereas we don't need to drive that system because it's out here as part of the initial conditions. So the initial conditions, we would say, favor metabolism right from the start. So here we have it again from Schrodinger, order from order. You can't have, you don't want a hypercycle. You don't want to drag life out of a chaotic mess. You need to have direct delivery. And there's one thing that, if you're not a geologist or don't know any geology, the one thing I'd like to remember as a rock type, and that is serpentinization. And so this is serpentinite, and you're going to see a few slides of this. You've all seen it in shop windows and so forth, on the sides of shop windows. You can see how fractured it is. This is kind of little engines of generation of hydrogen, actually, as the water permeates through this rock and serpentinizes what is the crust. And this is what in a kind of analogy with Maxwell's demon, this is the demon that makes the difference between this fluid, this fluid and this fluid, the serpentinization reaction. So just to remind us that this is the United Nations building. By the way, JPL said I really shouldn't show this slide because it was political. Well, I mean, here's the president, so I think it's beyond politics. But anyway, here's our serpentinite. It's, I'm sure you've become aware of this rock type. And what we're looking at is something called olivine plus water. Basically, here's olivine, magnesium iron silicate, plus water, generates some silica, some magnetite, so we've oxidized the iron now. Magnesium and calcium go into solution to make to give you the hydroxyl, the alkaline fluid, and hydrogen in solution. Now, and if there's carbon dioxide, a little bit of methane, and this is the pathway. The geochemical pathway. It goes from CO2, basically it goes pretty fast to methane, or fairly fast to methane, although you can see some of them, you can get formate in the reactions. So you can find this in a hot spring. Typically, hot spring, nothing to do with life at all, will generate methane, and you'll have a little bit of formate. You don't see any methyl alcohol, that seems to be pretty unstable, and go to the methane. So, well, we've talked about the methane, and I've just said that I don't think that this was an early reaction for biology, but nevertheless it's kind of there in the wings. The reaction that really takes place, I think, is the hydrogen plus the CO2 to acetate. So basically, acetate, it's CO2 plus CH4, by the way, makes you acetate. So to me, this is the key reaction, and in our lab, we can never make this. We've never been able to make this chemically. So we think that this really was the job for life. And so that thereby hangs the tale that we think that life, the beginnings of life was something that was a kind of microbe that was an acetogen, something that generated acetate from carbon dioxide and hydrogen. So we heard about the black smokers this morning. Here they are. And of course, as soon as they were discovered, they were predicted by Jack Corliss, and John Edmund worked with Jack Corliss. When these were discovered, predicted, by the way, in the Pacific, at 360 degrees centigrade, of course, the first thing to come to their mind was, well, maybe life started here. Stanley Miller didn't like that and wrote a letter to Nature saying it was ludicrous to think life could start at 400 or 360 degrees centigrade. I mean, yeah, I agree with him. But interestingly, there wouldn't have been black smokers on the early Earth. There had been many more of these springs, but they would have been 400 degrees centigrade. But they wouldn't be black smoke, because the only reason why you've got black smoke here is because it's acidic, hot solution. It's not because it's cooling, it's because it's interacting with the alkaline seawater. So you get the precipitation of this kind of so-called black smoke, which are things like iron, zinc, manganese oxides, and nickel, and a little bit of cobalt. So this basically, they provide the trace elements into the early ocean, and that becomes a reservoir, perhaps a supersaturated reservoir, of just the kind of metals we require for the first enzymes. So we've seen this. So this, I'm not sure if you can get this. This is the ocean floor spreading. Here's the actual spreading axis here. And right here we've got the magma. Here's the magma chamber. So the water comes down to just about its critical point, perhaps a little bit higher, becomes very buoyant, shoots back up. And as I think Jennifer said, they only last for about 10 to 100 years. So that's not very long. And as I say, they're up to 400 degrees centigrade. So it can't be here. But we've been working in mineral deposits in Ireland and Alpine ultramafic provinces, it's called. So we assumed that there should be other kinds of hot springs on the early Earth, and we predicted in 1989 that there should be alkaline springs. And fortune would have it, a PhD student was looking out of the submarine window as they were going to the mid-oceanic ridge, the mid-Atlantic ridge, and she saw that some kind of little wisps of white smoke material, and she stopped the submarine, told Deb Kelly, and they went back and they found this extraordinary structure. It's still the only main one to be found so far, but it's the Lost City submarine spring. It lasts for at least 30,000 years, pretty certainly 100,000 years. So that's or 10 to the 17 microseconds. And somebody also said yesterday, or perhaps this morning, that the interactions, the chemical interactions, we shouldn't think in our terms of us, our big bulky selves, and our time. We should think in terms of how long it takes to make these chemical reactions. So 10 to the power of 17 microseconds, I would think, is plenty of time for life to start. So what have we got here? So we've got that's made of calcium and magnesium hydroxide. It's up to 94 degrees centigrade, not too hot. 15 millimoles of hydrogen, so that's plenty of fuel, up to 2 millimoles of methane, and and they make compartments. So in the precipitation, there's always these springs, whatever the kind, always generates some hollow compartments where the fluid makes its way through in a kind of labyrinthine manner, and some of them seal off and so forth. And I think these compartments are all important because we must have compartments, I think, for metabolism to make any sense. Not only to keep the goodies, so to speak, inside, but also to use those gradients, which are pH gradients, redox gradients, and, of course, even a temperature gradient. So this is geochemistry. And one thing to say about it is, if it was geochemically easy to reduce carbon dioxide to methane, there would be no life. There'd be no requirement for it. It's a very fact that it's such an uphill task to add an electron to CO2 and then reduce it to formate and formaldehyde. And then, once you've got there, downhill it goes. But because of this, life can come in here as the catalyst to bring us up to formate or formaldehyde and then downhill. It's a kind of geochemical siphon. So, and here's what the methanogens do. So they make it easier. Catalysis lowers the activation energy required for the reaction, and also an ionic gradient is required to help CO2 be reduced to formate, and then after that it's fairly well downhill. But it's very complicated to get energy out of this. So I don't think that the methanogens were not early. But we think the acetogens were. So the acetogens now, they don't need an ionic gradient so much, well, except in the sense they need ATP, or adenosine triphosphate. And it's adenosine triphosphate that drives the CO2 up to formate and formaldehyde and methylene, and then downhill, and then you add a methyl group to carbon monoxide, which is reduced elsewhere, and you end up with acetate, which of course can take you onto pyruvate, and eventually can aminate. By the way, all these reactions taking place most easily in alkaline solution. So here, to put it all together, and let's think of this, you can think of this in all kinds of ways. It's a fractionation column, it's a hydrothermal flow reactor, but what I've done is to kind of dress it up as one structure here. But let me just remind you that here are the reduced molecules coming up. There's hydrogen, of course, a little bit of methane, some ammonia, molybdenum sulfide, soluble in alkaline solution, as are tungsten oxides, which I think is pretty significant because all life seems to require this molybdenum and tungsten at this early stage of reduction. And what I've plotted here really is basically the acetyl-coenzyme A pathway. So the CO2 comes from the outside. We think that we need some ferric ion or maybe nitrate out here to help to oxidize the reduced molybdenum site. So you lose an electron from molybdenum 4 to molybdenum 5, and then you've got a very energetic electron which can then reduce the CO2. And once you've done that, then you're off on that pathway up through onto a cobalt enzyme, which will take the methyl group onto acetyl-coenzyme A synthase itself, which is a nickel-bearing enzyme. Notice the importance of metals in here. We've already required molybdenum, iron, of course, iron sulfides as well, and the cobalt and the nickel. Once we've got here, then the acetate can be taken either by what is now a synthase, a thiol group, and the thiol can then be phosphorylated to generate acetyl phosphate, and the phosphate can then, with the help of other phosphate from outside, help to generate pyrophosphate from monophosphate. So this in the acetyl-coenzyme A pathway is ADP to ATP. Here we're using just monophosphate or orthophosphate to go to pyrophosphate, and that then feeds into general biosynthesis, acetogenic biosynthesis. I should say that there's also a methyl group here, and I think that methanotrophy was probably early as well. And what was the oxidant for methanotrophy? Probably nitric oxide or nitrate. So we've got two different kinds of schemes here. One basically doing the main job for the world, and that's spending the hydrogen fuel, and a little bit on the side spending the methyl fuel. So what do we do with this? Well, we can take it into the lab, and we can put hydrothermal solution on one side and ocean water on the other, and we can mix them. We can heat them up to 100 degrees centigrade. We can put them into a central reactor here with ultramafic rock, just like what's in the crust of the Earth, or the crust of Mars, indeed, or what was Venus, all the same rock. With a little bit of sulfide, and out comes the fluid. We then take this fluid and we take it to another lab, and this is in the other lab, and we inject this fluid into what we think of as a Hadean ocean, which had a little bit of ferrous chloride in, up to perhaps 10 millimoles from those very hot springs, this kind of somewhat acidic ocean, and we get this immediate precipitation, oftentimes sulfide, a little bit of silica, and so on. And in that reactor, we find we can make methane within actually just about 10 hours. We've got 16 parts per million by volume. So this is an abiotic reaction, very easy to do, and I think early life couldn't compete with geochemistry in this case. The hydrogen sulfide goes up to about 14 millimoles and then down to about 1 to 2 millimole, but again, enough to precipitate such a membrane. Here, just to remind us, is serpentinization, the requirement of serpentinization. So what do they look like? So we can now say, here's our main model. We're getting used to this now. Now we know that we've got an actual mound, a hydrothermal mound that's got compartments in it. Here are the kind of compartments. This is a chimney. Within the chimney, you get these small compartments made of iron sulfide or ferrous hydroxide or oxyhydroxide with plenty of what looks like catalytic surface, to my mind, anyway. So this is now the sequence, and what we've got here also is a propensity for waste. We can dispose of the waste. The things that do not play, the molecules that do not interact can just be taken off as waste. And of course, just like life itself, this is an entropy generator. But ordering, there is ordering going on within these structures. But outside, then entropy is generated through the waste, partly thermal, partly chemical. So putting the whole thing together again, making it slightly more reasonable to look at. Here's our hydrothermal mound, submarine hydrothermal mound. It's being fed with hydrogen sulfide, hydrogen, ammonia, molybdenum, tungsten, up to 120 degrees centigrade, pH 11, coming into this somewhat acidic ocean with all these electron acceptors on the outside and the metals and phosphate. And precipitating structures that are rather similar, mineral structures that are rather similar to the active centers of enzymes. And just to emphasize this point one more time, here's the protons on the outside, and we speculate that the protons can basically drive monophosphate phosphorylation to diphosphate, or perhaps through acetyl phosphate. So here's our proton motive force. It's all there. Everything you require for early life is there. All the metals, all the energy. And so what I want to emphasize is that biochemistry isn't just better geochemistry. There really is a discontinuity. And that discontinuity, because people have been very unsuccessful in generating, I think, organic molecules, because they think that all you have to do is get the recipe right, the chemical recipe, and we'll get life. I don't think so. We've got to have that proton motive force and redox gradients. So we can go to Gunther Wechtershäuser and Claudia Huber for perhaps one of the first and interesting structures. Now, this isn't so good as it looks, I admit, but what he's taken is a methyl group and a carbon monoxide and shown that on nickel iron sulfide, and indeed even nickel sulfate or nickel sulfide, then he can make acetyl thioacetate, basically, and hydrogen sulfide. He's done this at pH 6.4, which is a very nice little spike here. We haven't been able to reproduce that, but that could be our failing. But you could see that actually it's very well satisfied, this kind of reaction at pretty high pH. So again, I want to emphasize just how many of these reactions are promoted by alkaline conditions. So we take a closer look at our membranes, our structures, made in the lab, and there are some peculiarities to it, and of course anybody who's got any ideas about this, I welcome them. But this is the kind of membrane, so we're inside the membrane here, and you can see these what are called framboids, this kind of raspberry-shaped iron sulfides that grow on the inside. Then here we've got a mixture of iron monosulfide and something called gregite, Fe3S4, and on the outside is what the outside looks like. Absolutely extraordinary ordering of the outside, and indeed, even the inside looks like this. And we thought that might be kind of Chladni plate material. We're just not I don't know why these make such beautiful structures. I mean, they're much more beautiful and reliable than waves on a beach in sand. We would say that most of the action takes place here. The alkaline flow goes out, the acidic counterflow comes in, and most of the organic interactions or organic synthesis, we would argue, would be happening actually within the membrane. This membrane's about 5 to 10 microns across. Pretty wide for a membrane, and it's inorganic. So if we look again at this, what are the structures of the elements or the minerals that make this? Well, the main mineral to precipitate is something called mechanoiodide. And it's made, here it is, an iron sulfur rhomb. Basically, you put this together in such a way that it makes for something that's actually a pretty good electron conductor in that direction and a very good insulator in this direction. So we've got a semi-permeable and a semi-conducting membrane. So this is one of the chimneys. Here's a chimney again, and this is a kind of little offshoot, little compartment here, and here are subcompartments within the membrane itself. Now, if you look at that mechanoide, how similar it is to the actual active center of hydrogenase. And one thing we need to do is, if you've got H2, you've got to split into 2 electrons and 2 protons. So, and this is what hydrogenase does, and here's a structure, iron, sulfur, so similar, of course, to this structure here. So could it be that this was the first hydrogenase? Not a very effective one, but effective enough. And not only that, could it be that it's ready for co-option, so that if it were be co-opted by a short peptide, maybe that would make it even slightly more active. So if you have this at 80 degrees centigrade, this hydrothermal chimney, then within about 2 or 3 days, sometimes sooner, you get the generation of something called greigite, which is it should be Fe5NiS8. Oftentimes there's not nickel there, sometimes there is. If the nickel is there, it's going to be in this tetrahedral side here. So here we've put the 2 rhombs together. So we've got iron, sulfur, and behind it iron, sulfur, through 2 sulfurs to nickel. So this is just slightly oxidized, and it's the iron that's oxidized, not the sulfur. So this has nothing to do with the pyrite hypothesis, because in the pyrite hypothesis, it's the sulfur that gets oxidized. But of course, it's much better, I think, if we have the iron going back from, shall we say, 2 plus to 2.5 plus on average. Again, here's what the membrane looks like, made of this material. And look how similar it is to acetyl-coenzyme synthase, which is kind of where we came in. Here's the nickel side through sulfur, and here's now we've got a box or a cubane structure, which is extraordinarily similar to the cubane structure in here. So again, we're wondering, can this be the kind of structure that is actually acting as acetyl-coenzyme synthase type in the Vectorsizer-Huber reaction? So here we have that kind of structure. So what's next? Well, of course, what we need next, because what's easy to make, and as everybody's agreed, RNA is hard to make, almost impossible to make, but amino acids are easy to make in the lab. So we would say that's first, and here again, Huber and Vectorsizer has made some amino acids in the lab, and not only that, they can aminate them, and in this case, they've aminated these various structures with either iron sulfide or ferrous hydroxide. So that's the kind of thing that should be able to happen in our chimneys. And they happen at pH 9, and the yield is extraordinary. Well, if we can do that, can we, if pyrophosphate is available, and I should say that Deswart and Andy Pratt have produced pyrophosphate in the lab in a kind of substrate phosphorylation technique using ferrous iron as the catalyst and iron sulfide. And using that, then Yamanaka et al. And others have managed to actually phosphorylate and then basically dimerize with trimetaphosphate, in this case, glycine to 2 glycines. And that's not a bad yield at about pH, again, around about pH 9. If you lower the pH, then after 20 days or so, you can get up to glycine 4 or glycine 6. Now, once you've got to glycine 6, that's getting quite useful. Anything before 4 and 6 becomes useful. And one possible function for these is that they could then, through the amine group, directly bond to the delta negative on the amine group, things like cobalt and nickel. And could these be very inefficient, but basically kind of pigment peptides. And could they do, we know these structures exist, they've never been shown to be active, because I think they've never been tested in this way, but could these be, for example, similar to a transfer site for acetyl-CoA synthase and the site for reduction of the methyl group to methane? So we've got structures, again, that everything, as I say, is kind of on the plate here. So could we then have a beginning of a peptide takeover? Now, nobody's shown this. This is just paper chemistry, as people would like to point out, but here we'd suggest that nevertheless, ferredoxins are the, according to Eck and Dayhoff in a wonderful paper in Science in 1966, have the longest of all pedigrees of all metal proteins. Could it be the very first one was actually structured in a loop through hydrogen bonding through to a thiolated iron sulfide? So here's our cubane structure, and here's the possibility of it actually being thiolated, hydrogen bonded to the backbone. Notice it doesn't matter what the side chains are, just the backbone of a short peptide. Now, of course, these days, and probably fairly early on, it's cysteines, but cysteine is hard to make in the lab. It may be there were no sulfur-bearing amino acid side chains right at the beginning, but you will notice, if you people who worked on ferredoxins, the iron sulfide is always in a loop. So we'd say then, working with Wolfgang Nitschke, he suggested, for various reasons, including phylogenetics, that the last universal common ancestor, which we would put further back, but nevertheless, we'd say that the last universal common ancestor must have had molybdenum deuterium enzymes, had nitric oxide reductase, had nickel iron hydrogenase, and acetyl-coenzyme synthase, and carbon monoxide dehydrogenase. You have to have metals for this, and we'd suggest the metals were right in there, right at the beginning, and eventually were co-opted. So that all sounds, part of that is airy-fairy maybe, but the earlier part, I think, it holds up well. And now we've got the possibility that we've got a phosphate, and we know we can see phosphate and pyrophosphate in these situations, and that really would interact with the side chain, the backbone of short peptide to make a little peptide nest. And James Milner White and I call this a phosphate egg in a peptide nest. And this looks, I think you'll agree, very much like the P-loop. So here's how we would dress that up as a slightly longer peptide. And we turn this in, taking our cue from Henrik and Margareta Balchevsky. We take the idea that perhaps the first kind of pyrophosphatase was a proton pyrophosphatase, and that we could drive the generation of orthophosphate from pyrophosphate from orthophosphate by protons coming through the membrane, and having a magnesium ion as the catalyst, of course, because of the repulsion between the phosphates, this is required. But also, this is a little kind of entropy, to our mind, kind of entropy catalyst as well, holding things in because of the hydrogen bonding from the back of it, from the amine group through to the oxygens on the phosphate. So this would say, perhaps this is what the early proton pyrophosphatase actually looked like, and perhaps it was fired up basically by protons coming through the membrane from the acidic ocean. So here we have the kind of rough equation for this: magnesium phosphate plus orthophosphate plus the proton to give us your magnesium diphosphate. If we've got these short peptides, what we've done here is to put 4 or 5 mer peptides actually in the hydrothermal solution, the alkaline hydrothermal solution. And when we do that, we make even more better ordered structures. And these structures are, as you can see, just beautifully ribbed, both inside and outside. And glycine apparently gives us the best structure of all, for reasons we don't understand. So then we go back then to think where we've been with this, and what we've done is to take an idea, well, a paper from Andrews et al., who could show that you could get mixed acid fermentation via formate hydrogen lyase. And the reaction generates hydrogen and CO2 from formate and protons, and actually generates a proton motive force. And what is required here is one of these molybdenum enzymes and an iron sulfide factor as well, and the nickel iron as well. So what we've thought of, and of course this is something we're trying to do in the lab, is perhaps we could reduce it. Perhaps we can turn this around, make the protons come inside using nickel iron sulfide and molybdenum as the catalyst, and see if we can generate formate and perhaps formaldehyde from the inside by reacting CO2 and the protons and electrons to make the formate at pH 10 or pH 9 or pH 10. So this becomes really our holy grail. That's one question we'd like to answer. So what else does this kind of structure offer? Well, we don't know anything in detail about the RNA well, but Eugene Koonin and Koonin and Martin and Bask et al. Have suggested that, in fact, if you've got structures like this, then maybe the first RNAs, wherever they come from, act like viruses and basically can permeate through and start to make better replicators as we go through the structure. But also, if you were to make DNA in this series, in this way, you can have a polymerase chain reaction which is run thermally or convectively, because it's going to be cool on the outside and hot in the inside. So you're going to have a convective polymerase chain reaction to build up, shall we say, DNA lengths, and then thermophoresis or thermal diffusion then tends to drive concentrated molecules that are ionic into the coolest area of one of these compartments. So again, we haven't just got the we haven't just got the redox gradient and the pH gradient, but we've also got a thermal gradient that may help right at the beginning as you start to gain replication. So this is the way then we would see the very emergence of life, probably between 50, 70 degrees centigrade, 40 to 80 maybe. Hydrogen and methane as the fuels, molybdenum, tungsten absolutely required as catalysts, along with iron, nickel sulfides. And perhaps the first actual microbe, which we would assume was a bacterium, emanating from the spring, not into the ocean, by the way, but down into the deep biosphere, because I think it's basically a desert in the ocean, and it's a dangerous desert, as we've seen. But this first microbes would be generating acetate, or acetic acid, and then there'd be some more minor reactions that would generate, using nitric oxide as the electron acceptor, carbon dioxide and nitrogen and water from this reaction. And this would become, to our minds, the methanotrophic archaea. So if we put all that together, and we've heard other suggestions, for example, this morning about the Big Bang. When I go to parties, people ask me what I do, and I kind of finally cough if they really seem to be interested, and I tell them I'm working on the origin of life. I see them 6 months later, and they always seem to say, "Oh, you're the guy working on the Big Bang," and it kind of pushed us in to this idea that we make the comparison. And with Sean Carroll on hand, he wrote this lovely book called From Eternity to Here, which the older people in the audience will understand as a pretty good title. Anyway, he starts with a Big Bang, and it's a very high entropy, low entropy Big Bang, and here we are now, and we'd do the same thing. We'd have a Big Bang. We go from geochemistry to biochemistry, but we can't just segue one from the other. You've got to go through this discontinuity, and what helps us through the discontinuity, we would say, is the proto-motive force and chemiosmosis, which are on tap in the situation. And then after that, we get this various evolutions, parts of evolution, part of which has been covered by others. Of course, there's this huge yawning gap between metabolism and replication, and we don't deny that. One thing I would say, though, and that is that nearly everybody that's been talking about RNA and DNA and enzymes are on the other side of a canyon from me, I admit that, but we can see each other from either side. We're not that down there or up there. There is a lot in common between mineralogy and geochemistry and the very fact of the initial conditions that I think will eventually allow us to converge. And just to emphasize that, we've got 10 to the power of 17 microseconds, and I really do think that's enough time for life to emerge. Imagine what 200 postdocs could do for you in that amount of time. 24/7, of course, 365, as usual. That's it. Thank you very much.